Welcome back. Today we have a lecture on touch, one of the five main senses we're going to cover. And this will be a relatively short lecture, so let's go ahead and get started. So at this point in the class, we've covered smell and taste. And I like to sort of take a step back. Usually think we have our five main senses are smell, taste, touch, hearing, and vision, right? But if we really think about it, it's probably more complicated than that. So we can group senses in sort of three different ways. There's the number of physical stimuli you can imagine. So vision is light, that's the stimulus that we're looking at. There's the chemical senses, which we think of as smell and taste, and then mechanical as touch and hearing, right? Those are the ones that we're going to cover today. You could make a sort of bigger group: vision, hearing, smell, taste, and touch, right? But then pain, is that somehow different? It is sort of different if we look at it more. Mechanoreceptions such as balance, that's definitely different. Temperature, interoceptors, which is really talking about sort of our internal receptors. Things like how much oxygen do we have? Are we full? Do we need to go to the bathroom? Is our blood pressure high? We have all sorts of different senses really that are working on those as well. And here's a figure that I like in particular that really shows how many different ways you can think about it. So they kind of have, in the first column here, the orange blocks are the conservative ways you could think about it. The red is the accepted, and then blue is if you really just want to get as many as possible, right? So conservative is already sort of this 9 different one that we were talking about, or 10, I guess is what they have. But accepted, then, that would do things like with vision, maybe you can break that into light versus color vision, right? Or if we look at mechanoreception, now there's a whole bunch of different ones, and there's a whole bunch of different interoreceptors. And same with touch, we might be able to break that down. And the radical breaks this down even further. We're color, and we'll learn more about this. You could go from color vision to actually we have 3 different color receptors. So are those each their own sort of sense in a way, and we're really combining these? Technically, that's how it works. But it's maybe not useful to talk about it in such different ways, right? So just something to be thinking about. We talk about the 5 senses. Really, there's probably many more, but we're going to focus on the sort of 5 main ones. But we have to be able to think about all of them. Right, so we can't cover all of these in class. I want you to, though, for when we are back in class, to think about this question. Where do you think blood oxygen sensors project to in the brain? What part of the brain would really want to know sort of how much oxygen you have in your blood? All right, so mechanosensation, particularly we're talking about touch here, right? There are actually lots of different types of touch sensation. I don't want to dive way deep into this, but we can start to think about this a little bit. And what we know mostly about these different types of touch sensors are through mice. And mice in particular, but we have this as well, have 2 types of touch sensation that happen. You can talk about the glabrous versus the hairy, which are sort of weird names, but really you can think about it, for the most part, it's glabrous is sort of hands and feet, right, where we don't have any hair. They tend to be sort of extra sensitive regions, and they use specialized sensors. And then the hairy skin, which is obviously much more important for a mouse, but sort of the back of your arm and things like that. Most of your skin is covered with hair, and we sense different things using different sorts of sensors. If you look at here, the main takeaway I would say here is that with the hairy skin, most of our sensation actually comes from sort of sensing different types of movements of those hairs themselves. And we have different types of sensors that respond to sort of different strengths of touch. And then similarly in the glabrous cell, we have different types of sensors here. You can imagine these ones that come all the way up toward the top, the sort of Meissner corpuscles that get near the epidermis. And those are much more sensitive, whereas something like the Bastian's corpuscle requires more force to activate it because it's much deeper in the skin. And that gives a different sense. You could imagine, this could be light touch, and this could be sort of heavier touch. Now, if you really look at all of this, there's a whole bunch of different touch receptors, and these are the ones that we know so far. A few things to take away here. You can look, I always like to look at this column here. This is the different names of the sensors. Don't worry about too much there. This is, the skin type if you want to know it there. But the big thing to me for right now is to talk about, they each have their own optimal stimulus. So whether it's an indentation, stretch, vibration, this is an interesting one we'll talk about in a sec, skin movement, hair follicle deflection of different types, and this one's actually for noxious chemicals, right? Another thing to note, and this is the main reason I actually include this figure, how information is transferred in neuron. That's really, I think, a big thing that we're talking about as we're moving into this class, this part of the class. It's not always quite as obvious as you might think, right? The easy way to think about this is on or off, and that's sort of how this first cell works, right? What they're trying to show here is what sort of stimulus, right? An indentation, you start the indentation, the cell fires until you stop the indentation, and then it stops, right? But it's really more complicated than that. And part of this is to sort of save energy, and part of this is also to really define those start and stop points can often be key. So for example, this is another one that it responds to stretch, and as you activate at each one of these lines again, this is an action potential that they're measuring from this one stretch receptor. And at first it goes very fast, and then it sort of peters out and goes slower. Again, that's sort of, you could think of a way to save energy. But a key here is that when it turns off, there's this quick burst right at the end. This lets you know the stimulus is finished. And you can see that even further with this vibration sensor here, right? So stimulus starts, number of quick bursts, and then nothing. And then when the stimulus stops, a number of quick bursts. So how do you perceive this? The sensor, from what we can see, was really only active at the beginning and then at the end, this neuron at least attached to the sensor. But you're going to perceive this as vibration until it stops, right? So it's sort of a more efficient way, although you could imagine, what if there's a fire and what if one action potential sort of leaks through? There's a little bit more chance of an error, but really your body sort of sorts this all out. So your perception now, even though there's nothing happening in this neuron here, is that you're feeling vibration, even though there's no signal in some ways being transmitted, right? All right. So if we're thinking about is touch sensation sort of label line, or is it this combinatorial patterning, right? The sort of difference that we had between the sense of smell and the sense of taste and how they encode it. And the real answer is, and it's a complicator like most things, right? And it's a little bit of both, but I would say it's sort of more combinatorial sort of pattern encoding. So this sort of shows here, right? Again, and this is talking about the mouse, but we have similar sorts of systems, right? There's 3 different types of hairs based on length and width, and the idea is that different positionings of these will respond to different types of stimuli more likely, right? So if you have a poke, that's what this is showing here, then this, I believe these will respond most strongly, and then these other ones will respond less strongly. Not that they won't respond at all, but less strongly. So the brain is going to look at the combination, right, of all of these receptors. Did it see a strong stimulus from, and let's not worry about these names, they're very long and have even their abbreviations are long, right? But this first one is going to respond very strongly, but these other ones should still respond. Now, if it didn't see these other ones still responding, it's going to change the perception of that, how that is responding, right? And then sort of the opposite end of this is literally these two flipped around, right? So now this one that responded very strongly to a poke doesn't respond very strongly to a stroke, and the other 3 respond much more strongly, right? So then sort of flipping that and seeing these 3 receptors on, this one sort of mildly on, that is going to give you the perception of a stroke. So that sort of pattern or combination. And then, we can go slightly more complicated here, where if you have these 2 are very strong, this one is sort of on, and then this one's just not on at all, that is now going to give you the perception of a breeze, right? So the whole time here, we're looking at the same 4 different types of touch receptors. It's really just their pattern of activation that leads to the different perceptions of touch that we can have. So I like this, and again, if we were in class, much like the miracle berries, I'd let you try some of these out. So when we are back on campus, stop by my office, I have a big bag of these Sichuan peppercorns because they're an interesting way where we can sort of tease out just one of these sensors at once. Because what these sensors do, or what these peppercorns do, is they're a little bit different from the black pepper we're used to. If you've ever had Szechuan food, they use this a lot in their cooking. And these peppers have a chemical in them that actually activate just the vibration sensor. And there's actually multiple vibration sensors that respond to vibration of different frequencies. So there's just one of those that they activate. So they basically, if you eat a whole bunch of these, not even that many actually, like 6 or 8 will give you enough to get the sensation. Your whole mouth will start to feel tingly and numb, sort of almost like if your arm falls asleep, and it's sort of that buzzy sort of feeling that it has. These can make you there, and it's a very weird feeling, I think in part because you're really isolating, just activating one receptor, as opposed to everything else you would normally expect. You're activating multiple receptors in a pattern. Now you're actually kind of exposing that underneath it all, touch is kind of a labeled line, but your body doesn't quite know how to perceive it. So like I said, it's an odd sensation, although they're very tasty in itself, so most people find this enjoyable, especially when they're in food. Right, so normally we talk a little bit about, for each sense, sort of how this relates to neuroanatomy. But to be honest, we kind of know the answer to this already, right? The touch sensors are all going to go to your somatosensory cortex, the primary somatosensory cortex. And we've talked about this before, about how it's lined up in a similar fashion with motor, but sensory as well. Touch, where each different part of this motor cortex, sort of right on top of your brain here, has a different corresponding sort of region of the body that responds to touch. It's probably the simplest organization of all of these. Again, a key point to remember about here is that the parts of your body, like your face, for example, that have a lot more touch sensors, have a lot more space in the cortex as well. So just the reason for showing these mappings always is that it shows that something like the face as well, it takes up almost as much space as the rest of the body combined. And we'll talk about how this can relate to phantom limb pain in class. I do want to hit on one of these other senses that I think we would kind of put together with touch, but it actually ends up being sort of its own set of sensors, and that's temperature sensation. And this goes a little bit along with pain as well. So if you look up here, this is actually not all of the temperature sensors, but this is a good majority of the ones that we understand well. Again, not worrying too much about the names, just they're showing here, they all kind of look like the same proteins, right? But the interesting thing is they each respond to a different temperature, right? And they would each be found in a different cell. So then we could tell temperature fairly accurately. So for example, though, this TRPM8, if you look at this graph here, sort of, and it's in Celsius, so sort of around room temperature, it starts to respond, and as you get colder, it becomes more active, right, to a limit. And then at the other end of this, you can see TRPV1 here, so that responds to hot and quite hot already. So 40, that looks up for like 42 degrees Celsius, right? That's over 100 degrees Fahrenheit, and it's going to continue to be more active the hotter it gets. The reason to point those two out and what this figure makes is that these explain why we can get some sort of sensations that don't always make sense, right? So TRPM8 is what the menthol of mint binds to, and it activates it. So that's why chewing sort of mint gum gives you sort of a cool sensation, right? Is that it's literally activating the cool receptor. At the other end, TRPV1 is what capsaicin, that's the main hot chemical in hot peppers, binds to, and it causes that to become active. And so that's why we can get much hot sensation without our mouth physically being hot, is that it's activating this heat receptor. And you can see here too that most of the time mint doesn't make your tongue feel like it's literally frozen, right? Because look at this range. This is still a pretty normal range to be active in. This is temperatures that we're in all the time. Whereas this TRPV1 channel here, this is hotter than we're used to, right? So that's why this is much more, has a much stronger effect, right? Like if you eat a really spicy, you're going to react to that quite strongly. Also, this makes another point that sort of these middle ones, this TRPM8 that responds to here and this TRPM4 that responds to hot but not super hot, these are sort of your normal temperature sensors. These other ones that are at the sort of outer ranges here, the sort of extreme cold and extreme hot, are called sort of nociceptor temperature sensors. Nociceptor meaning sort of pain sensor. That's because these give you heat through pain. That's kind of what the signal is. When these are active, it's saying, oh, this is so hot, you should be in pain. And that's how it's telling you that. So they kind of classify those separately. All right, so that is all I have for temperature, or for touch. Thanks for watching, and I'll see you guys later in class.